So, what if a basic assumption in physics, one that's been hiding in plain sight for like 100 years, has sent us down the completely wrong path? Today, we're going to dive into a pretty radical idea, a new framework for understanding reality itself. And the way we get there? By first taking apart the very tools we use to describe it. Okay, just take a look at this incredible sunset. It really feels like a single perfect moment, right? Captured in time? But what if I told you this image is actually a time-traveling collage? Seriously, the light from that sun, it left 8 minutes ago. The light from those buildings, it left them just nanoseconds ago. But your camera caught them all at the exact same instant. So what did you actually take a picture of? That little puzzle right there is at the very heart of what we're digging into today. All right. So to really get to the bottom of this, here's our game plan. First, we're going to talk about 3 worlds, 1 reality. Then we'll look at the simultaneity problem. After that, we'll be setting the stage for a new way of thinking and peer through observation's window pane. We'll use that to rethink that sunset. And finally, we'll expose what's called a calculations ghost. Let's get started. Okay, so the first and most crucial step in this whole new framework is to, well, stop mixing everything up. The source we're looking at argues that we absolutely have to separate our understanding of reality into 3 completely distinct worlds that don't overlap. So world number 1 is the mathematical world. Just think of it as a perfect, abstract sandbox. It's a realm of pure logic, equations, symbols, all that stuff. And in this world, an equation is true only if it's logically consistent. That's it. It doesn't have to connect to the real world at all. Then you've got the physical world. This is, well, it's the actual stuff out there, the universe of cause and effect, where the laws of nature are in charge. And in this world, equations aren't just abstract ideas. No, here, they are models we build to try and describe what's really happening, like a light wave moving through space. And finally, and listen, this part is so important, we have the observational world. This is not the physical world itself. It's the world of our data about it. Think about the clicks on a Geiger counter, the numbers on a screen, the pixels in that sunset photo. This is the only world we can ever directly access. It's our only window. So, to sum it all up, the mathematical world is true if it's logical. The physical world, well, it just is. It follows its own rules. And the observational world, that's true if we can get the same measurements over and over. And the whole point here is that for the last century, physics has been just carelessly mushing these 3 together. And that brings us right to the core problem, the big issue this whole framework is designed to fix. The source actually calls it physics' original sin, and it's this: confusing the map for the territory. So what's the big mistake? According to this idea, it's when we take a tool from that purely abstract mathematical world and we start treating it like a real physical fact without any actual proof. And that tool, that huge mistake, has a name: simultaneity. Yeah, think about this for a second. The idea that 2 different things, say something happening on Earth and something happening on Mars, can happen at the same time is, well, it's a super convenient mathematical idea. But we can never actually see it happen. I mean, the speed of light gets in the way. And yet so much of modern physics is built on this totally unprovable mathematical concept, treating it like it's a cold, hard fact of the physical world. Okay, so how do we fix a problem that big? Well, the idea is to basically start over. We're going to carefully set the stage for how we describe physics, and this time we're going to make absolutely sure we don't mix up our 3 worlds. And the setup is a really clear 3-step process. Step 1, we create a purely mathematical tool. Let's call it an external reference. Its only job is to define one single moment, t=0, everywhere. Step 2, using that tool, we place all our objects, the sun, Earth, Mars, in their exact positions at that one single instant. And finally, step 3, we define the observer's window, which is basically the screen where all the data is going to show up. Now, let's be crystal clear about this external reference. This is not a physical thing. It's not some kind of ether or a God's eye view of the universe. No, it is just a rule we made up in our mathematical sandbox. It lets us say, okay, for this calculation, we're just going to declare that the sun, Earth, and Mars all exist at the same time right now at t=0. It's just a tool to get started. That's all it is.
So now that we've set the stage in the mathematical world, we can finally ask the most important question of all. What do we actually see in the observational world? And this right here is where this whole framework gets really, really interesting. This right here shows the core difference perfectly. On one side, you've got the simultaneous existence plane. That's from our mathematical setup, right? It's everything existing at that single moment, t=0. It's a cool concept, but you can never, ever observe it. Then on the other side, you have the equal arrival time plane. This is what we actually see. It's all the photons, all the bits of information that all hit our camera at the exact same time.
And this leads to a pretty wild conclusion. Our whole perception of now is basically an illusion. What we call seeing is really just information from a million different points in the past, all arriving at our eyes at the same time, projected onto a 2D surface. We are never, ever seeing the present. We are only ever looking at a collage of the past.
Okay, I know, that's all a little abstract, so let's make it way more concrete. Let's go back to that sunset photo we started with and apply this new way of thinking.
Here it is again, but this time we have the tools to really understand what we're looking at. And what we're looking at is not a picture of a single moment in time. This photo is the perfect example of an equal arrival time plane. Let's break it down. The light from the sun, that's 8 minutes old. The light from those buildings right up close, that's just nanoseconds old. And the light bouncing off Mount Fuji in the background is somewhere in between. Your camera's sensor gathered all these different photons from all these different paths at the exact same instant. See? You didn't capture a moment, you captured an arrival.
All right, so now let's see how this powerful new way of thinking can be used to poke some holes in one of the most famous thought experiments in all of physics, Einstein's light clock.
Yeah, you've probably seen this one before. It's the classic way to explain time dilation. You imagine a clock on a moving train that's just a pulse of light bouncing between two mirrors. If you're on the train, the light just goes straight up and down. But if you're watching from the platform, it looks like it's tracing a triangle. And that difference in the path is used to prove that time has to slow down for the train.
But here's the thing. This new framework reveals a fatal flaw. And the way the source puts it is just brutal. They were calculating the path of a ghost. A ghost. Why? Well, for two reasons. First, a pulse of light doesn't travel in a neat little line. It expands out as a sphere. And maybe even more important, the thought experiment never actually defines an observer. There's no specific place where the information arrives. So it's calculating the path of a light ray that could never exist, seen from a viewpoint that isn't there. It's confusing a math diagram with a real observation.
And all of this leaves us with one final, kind of unsettling question. If this framework is right, if everything we see and measure is just an old signal from the past that happens to arrive now, then what does the present even mean? Is the real physical now something we can ever actually know, or are we just forever looking at its echo?